Welcome to this explainer. Look, if you've spent any time at all trying to host AI locally, you already know the massive headache of figuring out hardware requirements. It's rough. But today, we're going to figure out how to stop guessing and start knowing exactly which AI models will actually run on your rig.
To really wrap our heads around the scale of this problem, just look at the raw numbers. According to Hugging Face, there are over 3 million publicly available AI models out there right now. 3 million. That is a staggering, completely overwhelming amount of choice. You might find a model that sounds incredible for your project, but honestly, finding the model is literally just step one.
Because how do you actually know which one fits your machine? Once you hit that Hugging Face page, the confusion hits you like a brick wall. You're suddenly staring at, 9 different quantizations, 4 different parameter sizes, and the worst part is there's absolutely zero indication if any of those specific variations will actually run on your particular setup. It leaves most of us completely in the dark, forced to rely on pure guesswork.
And we all know exactly where that guesswork leads. It's the ultimate time-wasting loop. You pick a model you think might work, you sit there twiddling your thumbs waiting for an 8 GB download to finish, you finally fire it up and, boom, out-of-memory error. You just burn bandwidth and time for absolutely nothing. But thankfully, there's finally a cure for this exact analysis paralysis.
Enter a tool called llmfit. It's a simple terminal tool, but what's really fascinating here is that it doesn't just guess. You run a single command, and it automatically detects your system's CPU cores, your RAM, and your GPU, even if you're running a massive multi-GPU setup. Then it calculates exactly how a model will perform on your specific infrastructure before you ever click download. It takes hundreds of models from its database and scores your setup against them using 4 main criteria: quality, speed, fit, and context. And the best part, it isn't rigid. It weighs these factors differently depending on what you're actually trying to do. Like if you're doing a chat task, the tool knows speed is absolutely paramount. But if you're doing deep reasoning, it's going to weigh quality much higher. So the exact same model will actually rank differently based on your workflow.
Now, speed really just comes down to how fast your VRAM can feed the GPU. Since every token generated means reading the entire model's weights off your VRAM once, memory bandwidth is everything. llmfit identifies the real memory bandwidth from your specific card and runs that against the model size to estimate your tokens per second. And hey, if you're running some obscure GPU that isn't in their database, no problem. It gracefully falls back to constants for CUDA, Metal, or ROCm, so you're always getting a solid estimate.
Part 1. The microboard stress test. Let's see what happens when we test tiny hardware. To really see how this tool behaves, we decided to stress test it in the lab on some comically underpowered hardware. We grabbed a first-generation Raspberry Pi from 2012, single core, 700 MHz, just 512 megs of RAM, and then a LoxFox Pico Ultra W, which is this tiny embedded board built for security systems with a mere 256 megabytes of RAM. These boards are incredibly weak, but they run Linux, so we could actually run llmfit. And the recommendation it spit out, honestly, it kind of blew our minds. For both these tiny, ancient boards, the tool confidently suggested DeepSeek R1 as the absolute best choice. Just for context, that is a massive model with nearly 400 billion parameters requiring 230 gigabytes of disk space. The math on cramming that into a 256 megabyte board is just completely bonkers. To be fair, at least the tool was dead honest about the expected speed for that massive model, clocking it at a highly painful 0.8 tokens per second. But yeah, the accuracy definitely broke down on this ancient hardware. For example, on a smaller model, the Falcon H1 Mini, it predicted a blazing 241 tokens a second. Reality? Predator tests showed it chugging along at a sluggish 0.3 tokens a second. So clearly, for a decade-old microboard, the math has its limits.
Part 2. Testing everyday laptops. Stepping up to real work machines.
Since llmfit clearly isn't built for tiny 2012 security cameras, we moved to something people actually use for real work. We tested a 2015 13-inch MacBook Pro, running 8 gigs of DDR3 RAM and an Intel Core i5. Here, we finally start getting usable, realistic recommendations. It handed us a list of small models, mostly 8-bit quantized, and estimated speeds between 40 and 170 tokens per second. Now that might be a tad generous for a decade-old Intel chip, but we are absolutely in the right ballpark now.
And this is exactly where the filtering feature really shines. When we filtered specifically for coding models, the top pick shifted to QN 3.6. Specifically, the 12 billion parameter version crammed down with a heavy 2-bit quantization, giving an estimated speed of 2.3 tokens a second. Sure, it's slow, but honestly, it's a very fair trade-off if you absolutely must run a 12 billion parameter model on an aging laptop. This brilliantly illustrates the leap to modern hardware, jumping up to an M2 Max MacBook Pro with 32 gigs of unified memory. llmfit totally understands Apple Silicon. The best general model was a DeepSeek R1 and quantization, but more importantly, filtering for coding correctly identified the 12 billion parameter Llama 4 as the top pick. If you know anything about MLX setups on Apple Silicon, you know Llama 4 is an absolute beast. It proves this tool really knows its stuff here.
Part 3. Pushing the RTX 5090. Time for the ultimate lab test.
We unleashed llmfit on an absolute unit of a machine. An RTX 5090 GPU, 64 gigs of DDR5 RAM, and an Intel Core Ultra 9 285K. On a rig this beefy, you expect the big models. And sure enough, we started getting perfect scores across the board from massive heavy hitters, particularly the Quinthen 3.8 series.
Even when we filtered just for coding models on that 5090, the Qwen 3 series absolutely dominated the top spots. But this is where playing with the tool really pays off. We kept the coding filter, but sorted the results by context size. Suddenly, a totally fascinating alternative surfaced right at the top of the list, NVIDIA's Kimi K2.7D flash model.
As the source analysis noted, Kimi K2.7D Flash is actually a much better, closer fit for that specific coding task than the default Qwen models. It proves a really vital point here. By actually utilizing the advanced configurations, filters, and community leaderboards built into this tool, you can easily bypass the default options and find the exact right tool for your highly specific workflow.
Ultimately, this explainer shows that the days of blindly guessing your way through local hosting are totally over. You don't have to just cross your fingers and pray a model works anymore. You can step out of analysis paralysis and let the math, system detection, and real VRAM bandwidth calculations do all the heavy lifting for you.
Now that you know exactly how to perfectly match a model to your machine's actual capabilities, I highly recommend firing this up on your own rig to see what fits. So, I'll leave you with this. Will you let your hardware safely dictate your next download, or are you going to keep risking an out-of-memory crash in the dark? Thanks for joining us, and happy hosting.